Hey,
Hey, well, we did it. We finally got this thing to print and got it working. This is a five-fold quasi-crystal. Just one of the many cool things we're working on here at the lab for the 3D prints and whatnot. So Michael is here with me. Um, where are you, Michael? There you are. I forgot tonight was this thing in Somerville. I said on Twitter I was going to go to it, so I'm not there. It's already passed. I noticed it when I was going through all my closing tabs, and I was like, "Oh crap, that was tonight." I already planned the stream, and we had already made other plans earlier because I didn't remember about this. So I'm sorry about that to anyone who showed up looking for me there. But I think maybe we're gonna hold. Maybe we should hold an event where we have like an open house here at the lab or something, and like a where people could come forward and share their own cool stuff or what they're working on or pieces of whatever. I don't know. I thought about it. It might be a little too crazy and open up to the intel agencies to really get in our doors, but I feel
we
like
can
they
do a
might,
live stream.
with some of the people that have visited and over here in the past few months. Sometimes I wonder if we haven't already been paid a visit.
Oh yeah, we had a Rothschild here. Remember that?
Yeah, that guy, interesting. Yeah, is that your real last name, or are you just saying that to like impress
No,
people?
he was legit. I could sense his dark aura. like
Yeah,
I'm not very sensitive to that stuff.
but a couple things we've been working on is replicating some of the Vem drive, which is David Perz's kind of warp engine, and getting the idea from David Chester recently asked the chatbot what was it what's the chatbot there, the the one
ChatGPT.
that, not Chat GPT, but the one that writes the let me just find his message here. Oh, I should have invited Ken for an update. David Chester said that the oh wait, it's on a different text message app. Sorry, and it's lost in the chat now. It's the one that writes the essays for people. But anyways, he asked, Claude 3 Opus. Sorry, Claude. I couldn't think of Claude. That's the one that Jay from Project Unities was using to write all those weird papers that he was saying, like, did this thing solve, you know, ancient, he tried to get like the AI to solve these ancient mysteries and other like physics puzzles and mysteries. So I don't think AI is that powerful yet that it can quite.
No, it still makes up article titles when it tries to cite things. It doesn't know the context for any of that.
Yeah, yeah. So yeah, we're using an for the 3D printer that we're using. Actually, I broke one of the 3D printers doing this. I was thinking this could be a good first start if someone wants to volunteer, from the chat to buy us. It's only $68 plus shipping for a new hot end. I'd like to replace the hot end in this printer. We've replaced the thermocouple and the other stuff, but this thing's old. It's beat. It's gotten a lot of runs. I'd just like to buy a new one. So if someone wants to pitch in and help us buy some equipment, that would be cool because then I don't have to order it. Um, but yeah, I'm gonna almost make a wish list on the website page where people can like buy us lab equipment, and as it arrives, I'll check it off the list. It's always that good. We have four of these printers, so if two people or three people buy us, the same thing, it's not, I guess, that big of a deal.
So
Um,
anyway, Jeremy, that quasi crystal thing. Let's talk more about that stuff, right?
yeah, yeah. The quasi crystal is interesting because it's got the unit is the golden rhombus.
That's interesting, by the way, because I noticed that some the what do you call it, the LK99 crystals that they've been showing off recently have that. almost exact rhombus-shaped crystal to them. So I wonder if if you quench the LK99 crystals really fast, if it forms into a quasicrystal lattice or a quasicrystal metal lattice or something.
Interesting. Well,
I just noticed we saw a lot of rhombohedral crystals like that as well in our testing with LK99. By the way, you pull up SCTL's YouTube channel. So it's not dead. It's not dead yet. They demonstrated what really looks like quantum locking. SCTL, LK99. Yeah, this is the second one up, not that one. The one above that's obviously not the effect they were going for. But look at this; it's just pinned at that location, and then it's not, and it's not touching the surface or anything. It's a good distance away, and so they get it nice up and close, and it stays there. And I mean, it's possible it's going through some sort of paramagnetic diamagnetic transition at a specific amount of field strength. But yeah, it's a peculiar effect that they're seeing here. There's definitely something weird going on that's worth more investigation. I don't know if they haven't been able to get superconductivity off of the surface, so we'll see. But I mean, that looks to me like quantum locking. A lot look at that. There's definitely there's a reasonably large space in there. It's not.
Yeah, I don't know.
And it gets pulled both ways. It's pushed away from it, and then it's also pulled as they move it away.
Yeah, right. That's pretty wild. There's there's definitely a visible space there between the face of that square magnet and the.
And there's two other things it could be. As I said, if there were a material with a paramagnetic response up until a certain field strength, and then beyond that field strength it has a diamagnetic response, then it would settle at some location at some distance, some specific distance from the magnet. So what you could do then is see if you use weaker magnets, does it not get flux pinned at all? Or if you use stronger magnets for that matter. Well, no, stronger magnets weaker magnets. And then the other possible thing it could be is if there's some sort of weird magnetic field structure in that piece of material, and it's being held vertically like that, then it might not be free to rotate. And so typically the potential wells for magnetic fields are saddle nodes. But if you have a constrained optimization problem on a saddle node, you can still have a local minimum. And so it might be getting stuck in something like that. So there's a bunch of magnets that will keep their distance from each other. And then when you twist them, they lock together. And that's because they're held in a door frame or whatever. So they'll prevent a door from slamming, but also they'll stick together if you twist them. And so typically those are two flat doors, and they're held from rotating and stuff. And so that's
these the magnets that do weird things to the near field, because that's kind of what we're trying to do, right? We're trying to make these longitudinal modes.
No, not exactly. Not in this case. It's just standard fields, but you're patterning them in such a way. Maybe we can find it online. I forget. There was magnetic patterning. Just look up magnetic patterning.
Well, anyways, what I'd said about that Dave Chester had gotten that Claude 3 to ask it. He asked it how would you create these longitudinal modes, and he said it was you might want to try fractal geometries like the Koch snowflake, which I thought that was hilarious.
Yep, I mean that's what David Paris is doing. Let's see. Oh, I think I found it. Oh no, that's Hallbach arrays. I'm looking for that thing. Oh yeah, here's the inverter magnet. That's here's an example of a pinned magnetic structure. Although there were better examples.
put it in the private chat so I can bring it up for sure.
Sure. Here
Oh,
you go.
This is a good teaching opportunity, and I just want
Yeah.
to give a shout out to the crowd. Mike wants to know what's a near field, Michael.
So basically, the near field, so like electrostatic or magnetostatic fields are near field effects. They don't propagate as waves in the far field. So, formally speaking, mathematically, um, wave equations have hyperbolic PDEs associated with them, and um, and stuff that behaves as a near field effect typically has a parabolic or elliptic equation normal to the surface, and sometimes it will have a wave equation along a surface. So like xenic surface waves, surface plasmons, those are waves on the surface that they're attached to, but normal to the surface, they fall off with distance exponentially. Um, and so they're pinned to some boundary conditions, and then um, the PDE solutions available for them vary depending on which axis you're looking at. And typically, so yes, static fields are sort of a near field effect because they don't propagate into the far field. And then if you have a dynamic field, if you have something that's putting off AC signals, um, the near field will fall off exponentially with distance, whereas far field will fall off with an inverse square law. And so there's also some ideas. Well, I mean, Yang-Mills theory is the particles themselves are a sort of near field structure. It's but that gets into solitons and nonlinear PDEs, and that gets a lot more complicated. So, I mean that's like a whole class. But yeah, look at that. There's definitely like a little distance between there. They do a whole bunch of these tests, and then they can like remove it from pinning. So, Jeremy, I think I sent you the correct link. I'll just triple check that. Yeah, Jeremy, I sent the link. Oh, and there's a few other cases I recall now, so I'll look up those. I'm not getting any sound.
Should I play the sound?
I'm not getting any sound in the StreamYard, but maybe it doesn't need the sound. I mean, the idea is.
Should I play the?
Oh, you know what? The LK99 video wasn't getting any sound. I was looking at the YouTube.
No, it didn't have sound on that video, but I can put sound on this one. Do you want sound on this one?
Maybe it's not necessary. Here, let me see if I can pull it. Cody's lab did this too.
So what's he doing? All right, so very strong magnets, and he makes...
Yeah, look, at modeling a gas with magnets. Cody's lab did this. I remember this one. This was a good one. Yeah, and so you see, as you pull these magnets, as you put these magnets here, they push away. And then they snap together, and then... Yeah, take a look at this. See, there's two magnets there. And so actually, oh, okay, so that sticks to that. Yeah, watch. Well, maybe not yet. There we go, yes. That's how you, yeah, I recall now. Yeah, so there's the central magnet that attracts it, and the other ones repel it. And so when you bring it close, it has a local minimum. And the reason that it sticks in that local minimum is because the table is restricting the angular position. And so a saddle node becomes a stable distance between the... So yeah, if there's an effect like this going on in the crystal lattice where there's certain domains that are paramagnetic, certain domains that are diamagnetic, you can get a field that gets pinned this way. And it's not actually superconducting flux pinning. And what I'm suggesting is it's possible that the string that's attached to the piece of LK99 is preventing it from rotating in a way that would like
Like the flat magnet on the table is
wouldn't
prevented
snap
from
together
flipping.
otherwise.
Like on the table, that flat magnet's prevented from flipping over. If this was in free space, it wouldn't be restricted like that. You know?
Exactly. Yeah, and so it would jump to one or the other end.
Right.
And I think I dropped the Cody's Lab video in the thing too. Let's see.
And is this like the near field and far field, like that gap, how it's attractive to one point and then repulsive?
Yeah, and this is why you can think of the strong force as something akin to this, and the weak, like, so you have some repulsion between these things from the electrostatic force, and then the strong force is some sort of, well, I mean, you can think of the strong force as like a sort of Casimir force, where if the protons and neutrons are effectively conductive droplets of quark gluon plasma, then in an abstract sense, at least, as you bring these two droplets close together, you're going to get a Casimir force between them, mediated by all of the unified fields. So you're going to get quark exchange mainly, and ultimately, if you think of it as a Casimir force, I mean, it doesn't change anything about the equations at the end of the day. And so, I mean, there's some analogy there, at least, that's interesting. Certainly, if you extend the magnitude, if you see what the magnitude of the Casimir force would be at that length scale, it is comparable to the strong force, actually, if I recall correctly. I think that was Larry Lemke's thing originally. I think he mentioned that first, to my knowledge. I'm sure maybe other people have mentioned that before. I just wanted to cite things properly. But it's interesting to think of the strong force as a possible extension of the Casimir force.
That's a great way to visualize it and stuff. So yeah, and this is like.
So I would jump ahead because this video is kind of long, but see, so here he's got. You see, you can think of these all as like molecules. So like if you put one in that has the opposite charge, it sticks to 3, and then it forms a little separate molecule. And these things are bouncing around differently at different heights, and yeah, it's different pressures in the gas. They're closer together at the bottom. So yeah, I mean, roughly speaking, if you jiggle this around, you can think of it as a gas, an ideal gas model, sort of. And yeah, you can do all sorts of crazy stuff with this. But yeah, I mean, all of these magnets are constrained by these 2 panes of glass. So because they can't rotate, there's these minima that are stable, where otherwise they would, in 3D space, they wouldn't be.
Yeah, right.
Yeah,
and so depend on each other.
Yeah, and so this is there was an even better video with patterned magnets. Maybe I can dig that up while you talk about some of the other stuff that's been going on, Jeremy.
Wait, say that again?
Oh, maybe I can. So there's another video. Maybe I can dig up that other video while you talk about all this other stuff going on.
All right, yeah, go find that video. But this is really cool. It kind of like helps me visualize, how water might work inside of, and how waves would develop within that structure,
Oh yeah, and there's one guy that did magnetic vibrations on a thing. That was pretty neat. That kind of, where did that go? Nah, that one's not.
This was a cool thing. This guy is generating quasicrystals with just plane waves. So he does these frequency vibrations on like a Chladni plate and is able to make these.
I wouldn't call those necessarily quasicrystals.
But yeah, zebra crystals and stuff.
Oh,
I wonder if you could 3D, basically like induce. I had this idea for years about, I don't know if anyone's actually doing this, but making crystal structures by, inductive vibration.
That's something that might be interesting to try with the LK99 samples.
Yeah, electromagnetic cooling.
Oh, speaking of quasicrystals, one thing I want to try with that is there's something called potassium look up the nanohydridorenate ion. That's what we're looking at recently, or one of the things we're looking at.
No, we'll get one of those like high school kits from like the toy store with the crystal growing, one of the crystal growing kits, you know.
Here, I put it in the chat.
And we'll put it inside of
Non-hydrogenate.
we'll put it in a chladni plate as you mix the chemicals in it, and then it will start forming crystals.
I don't know. Maybe. I think there's
Someone got a
more valuable
chladni
avenues.
plate can try this experiment. We don't have a chladni plate or the time to really run this one, but someone does.
Yeah, there's better uses of our time. Check out non-hydrogenates. So I remember that guy from NASA that you used to talk to, who passed away.
Before we get into that, let's talk about Charles Bueller.
Go ahead. Yeah, I'll find that thing. You talk about Charles's thing.
So, guys, this is from the NASA spaceflight.com forum, and people are talking about Tim Ventura's interview with Charles Bueller on this propulsion device. There's lots of interested engineers, looking into this now, and apparently we've gotten Elon Musk's attention to some degree. Is he at least acknowledged? Apparently he's got like a some kind of space program now. Like he's got
some investment fund, but I think it's best not to talk about that for the moment. We'll see how it plans out.
Yeah, so I know that he's not. I'll see what's going on with him. But yeah, finally, NASA is getting this information out. We're glad that they chose, APEC to do it through. We're proud to serve this community with the interviews that we've done and the information that we brought forward, however actionable and interesting it may be to you all. So, but in any case, the biggest step is producing electrets and ways of making, trapping electric fields and electric charge. And this guy's got this really cool way of doing that inside of different materials, mostly like these glass or quartz or crystal breaking arrangements where he runs super high voltage through them.
Yeah, doesn't that guy have like a multi-megavolt electron beam that he runs this stuff under?
Yeah, because this is like super dangerous to do. He's got a 10-inch Tesla coil, I think. And,
I think there's some videos of it, of the, let's see.
Yeah, he's got stuff on his site, but it's all outdated,
Oh, this one's cool. Radiation field shielded GoPro in a electron beam irradiator. Let's see, copy that link. Check this one out. Oh, you got the videos. Cool. I like this one in particular.
So this is like a welder or something, right? It's like an arc welder on the end of an acrylic rod.
No, it's not. That's just a grounding wire with a. That's a grounding wire with a nail at the end of it, and you hit it into the thing, and then the mechanical disturbance to the acrylic is enough asymmetry that it induces an electrostatic discharge.
And
it all goes.
He doesn't use high voltage across this?
No, he ran it through an electron beam already.
Oh.
And so the electrons get deposited from the electron beam in the solid plastic.
Oh.
And so this piece of plastic, it's a monopolar electret at a couple megavolts. It's like a very strong electret. And so if you check out the video that I added, there's like some pieces of calcite or something, and they're probably irradiating them so they can do NMR studies on the calcite. And it's cool because when you send stuff through the electron beam, check it out. I put it in the thing anyway.
It looks like roots or something, man.
Actually, look at this one with the swirl. You can you can put like aluminum foil on top, which blocks the electrons, and then in the other locations, the electrons go into the plastic. And so
it's not energized in the spots without the arcs, right?
Exactly. And so, yeah, check out this other one with the what do you call it? Yeah, I added another link to the StreamYard.
Yeah, let's 3D print electrodes. Maybe that would be.
So we're trying something a little different for electrodes.
We have a different method for producing them. So I have an idea, and I don't think we're going to share it publicly.
Well, no, I think we can. It's simple enough.
See if it works first.
Yeah, I mean that might be wise. I mean, at least. So basically, if you have a liquid and you put an electrostatic charge on the liquid, because it's not a solid, all of the charges can migrate to the surface. And so what we're interested to try is if you have some solvent with plastic and you put an electrostatic charge on that solvent plastic mixture, then you can shoot that out of a sprayer, and you can, in principle, if it's going fast enough, you can spray a surface with these particles that are all charged the same. And ideally, like, some of them will hit the surface, but I mean, it might be pretty low efficiency. And the idea is you can build up a layer of material on the surface, which is drying out as you're spraying it and as it hits the surface. And so it's retaining that charge within some volume, and then it hits the surface and it dries out completely. And so there's a ring of charge on the surface that's deposited each time. And if you have subsequent droplets, they'll spread the charges out a little bit, but not that much. And so we're hoping that if we produce an electrode this way, we can get a nice surface and then very, very quickly stick it to the other surface. And so we have a monopolar electrode on one side, and we'll have a very high dielectric constant material on the other side, with like CCTO probably, and as highly concentrated as we can get it in an epoxy.
So this is the electron beam. We've seen it in the last video, in the last seat part right there, and now they're firing it at this thing on a rotating, carousel.
Yeah, and these excess electrons, you can use them for NMR and EPR, and they have different properties and things. Obviously, they can come out of the thing pretty easily. So, Jeremy, I sent the other link there. That one's cool. It's got quartz. It's got a.
If only there was a way to hit him with muons.
It's hard to generate. It's hard to generate muons in any quantity.
I know. It is, but if you could, say it. Oh,
so anyway.
Oh wow.
Yeah, these store a lot of energy. It's not very practical because it's single use, but it looks nice. Yeah, see, there's like a bunch of calcite crystals, and they just have ordinary salt, and like you can make salt like blue with radiation and stuff, and I think you can do the same thing with quartz if you introduce enough defects in the lattice.
They put the
or something. So yeah, look at this. Like those calcite crystals are already starting to scintillate, and they're not even through the beam yet. Like they start glowing like ridiculously bright. Oh, maybe that was just the light they went over. My bad. They're not there yet.
Yeah, they're not there yet.
So basically, like, you can pay this company, like, what was it? like $900, and they'll take your tray and they'll put whatever samples through the thing. And now they're glowing so bright that they're throwing off the camera. And look at that. That's the electron beam. It's so powerful. It's creating Cherenkov radiation. And so, yeah, and you can see the cameras detecting the particle collisions on it now, because it's.
So they just put the GoPro right. The GoPro.
Yeah, obviously they have to radiation shield it so it doesn't like fully break. But look how bright those things get when they scintillate.
Wow! Look at all the static on it. Now it's like full beam, and it just passed through it.
Yeah, wow. It's pretty wild. And then there's like a piece of plastic foil or something that looks like
charging your crystals, man.
Yeah, right.
Yeah.
I mean, electron beams like that are scary. That level of radiation will give you cancer for sure.
Oh, I know. Look at all the excitation.
Radiation poisoning. Yeah, they're still glowing, and
that's little trails.
Probably, that's scintillation. That's probably still due to the electron beam at a distance.
Are we still live? Okay, cool.
Yeah. And so, like, a lot of crystals will scintillate like this. when you put and that's how a lot of modern Geiger counters work. They have a scintillation crystal and they count the photons emitted. Wow.
That's cool. Look at them glowing. They're glowing like bright red coming out.
Yeah,
of there.
they're phosphorescing a little bit at least. And that's a good transition, actually. We learned a little bit more about, well, I wouldn't necessarily say it's Ormus, but the real thing. So I was talking to a guy and he was saying like orbital rearrangement has to do with other spin states that are stable within a molecule. And so we found a bunch of this stuff at the NMR conference we went to. Want to talk about that?
Yeah, the NMR conference. Where was that?
Oh, Asilomar conference ground. It's the ENC conference. ENC. Yeah, there we go. Right. This thing was amazing, and we met like world-class people.
Bruker were there.
I think they did not take Mark seriously. I think very few people reached out to us via email afterwards. So,
Mark can do that at those types of places.
Yeah, I mean, I tried to keep it scientific, but there wasn't much. But we learned a ton anyway, so that's worth the trip. But yeah, pretty standard scientific background and stuff. And so yeah, they were talking about how ever since like the space program, so like in the space program, they were trying to use hydrogen as a fuel, and so they learned that if you have two hydrogen atoms and the electrons have spin states in the same direction, then that's an energetic state. And in fact, if you're trying to take hydrogen and make it into liquid hydrogen, then the atoms need to be reduced to an energy state. So you can only have liquid para-hydrogen. You can't have liquid orthohydrogen, or it will boil itself when it comes into contact with surfaces. So the symmetry breaking from the surfaces, like rust on an engine, the symmetry breaking was enough to relax it into its para-hydrogen state. And once it became para-hydrogen, it would release thermal energy. And so like a lot of the early failures in rocketry were because of apparently figuring out this orthohydrogen to para-hydrogen thing. They were trying to make a hydrogen tank, and then it would just spontaneously blow up at some random time, associated with like a cascade of orthohydrogen to para-hydrogen transition.
Really?
So another interesting thing about this that we learned is that if you have a thing of liquid hydrogen and it is less than 50% para-hydrogen, it is necessarily not entangled. But if you have something that's greater than 50% para-hydrogen, mathematically speaking, it is necessarily entangled. So if you have a tank of pure para-hydrogen, it's a inherently quantum material. It's necessarily entangled, which is pretty interesting. And that's just due to something called Ramsey theory, which we've spoken about before. Ramsey theory is a graph theoretic thing. Yeah, let's see. It's a combinatorics thing, exactly. So the classical explanation for Ramsey theory is if you have 6 people, then either 3 people know each other or 3 people do not know each other. One of those has to be true. And you can see that, but if you draw the graph of all the connections between people, either each person knows or doesn't know the other person. And so if you draw that graph, you can prove to yourself, if you have these 6 people, one of these things must be true. And it's sort of for this reason that when you have only para-hydrogen, then it's restricted to a certain set of quantum states. And those states that it's restricted to must have some entanglement, which is fascinating. And so para-hydrogen is actually used in industry for something called hyperpolarization, which is an alternative technique of orienting nuclear spins that is similar to the dynamic nuclear orientation that Mark was trying to do. And it's very efficient because the spin diffusion of hydrogen is the greatest for any of the elements. And so you can get some spin entanglement, or you can get some nuclear oriented spins in the parahydrogen, and you can immediately transfer it to your sample under cryogenic conditions typically.
Is this a key to the hydrogen? Because Ed Fouché used to always talk about hydrogen crystals.
No, that's more the non-hydrogenate things. Check that out.
Yeah. All right. This is a good transition into that.
Well, I'm actually, before we do that, singlet oxygen. So this is basically, if we jump back to the parahydrogen, orthohydrogen again. So yeah, the simplest case was, so I was talking to a fellow and he was saying ORMUS is simply this. It's you have some standard spin state for a molecule, and then you switch it to some either slightly lower or slightly higher energy state that is metastable. So orthohydrogen is metastable, and parahydrogen is the minimum energy state of that system. And so, I mean, I don't know, I don't really believe a lot of that I hear about this ORMUS stuff, but
it's like snake oil, though. A lot of it is not really.
Yeah, it's definitely, that's the thing though, like a lot of these things where the new age people gather around it, like there's a grain of truth somewhere there, and then like there's so much BS around all of that like if you just Google the thing, you're not going to find the real thing. But the spin thing makes a lot of sense, because now you can get, if you reorient these spins, especially with like parahydrogen, they were saying like a lot of these ORMUS don't have the same spectrum. If you were to try to do optical spectroscopy on these, they don't have the same spectrum that they usually would. And indeed, spin flips would alter the spectrum of the material. I don't know to what degree. I think a lot of the people with ORMUS claim that there is no optical spectrum from these materials when you excite them as a plasma, like at all. And I don't know if I believe that, but certainly if you have like fully entangled parahydrogen, like it would not be
at all, or is.
Yeah, so I don't know about that claim either. So like that seems like
because they'd have to do that, and then
like I've heard this about ORMUS from multiple sources, but I don't know about that particular claim. What I do know is if you have these different spin states, you can certainly alter the spectrum a little bit. In terms of parahydrogen, maybe if it's like completely entangled, you could get rid of the spectrum somehow. Or at least if you introduce energy to it to try to get a spectrum, then it would no longer be in its ORMUS state, I suppose. So maybe there's situations like that where trying to get a spectrum out of it destroys the material. And so that might be more like what they're trying to say. It's like, if you introduce energy to this thing, it destroys the state that it's in. Oh yeah, we got that ARV. RIP Mark McCandlish. He was good. So anyway, singlet oxygen is another example. So if you, so a spin singlet, I forget what the detail is, but it's some excited state of the spin states. And so normal oxygen isn't super reactive, but singlet oxygen is scary reactive. It's like fluorine or something. You don't want to be dealing with singlet oxygen. Oh, cool. So the triplet state is the ground state of O2. That's interesting. So that would explain why oxygen is paramagnetic as well, because it's a spin triplet state. But anyway, yeah, here's all the quantum modes that it can be in. And so oxygen forms these kind of ORMUS things as well. Maybe if that's what ORMUS is.
If that's what it is, man, I don't know. I think there might be some truth to this with the alchemy, like something that the ancient alchemists figured out or knew, some knowledge that was passed down.
Well, all I know is like they claim that like you have higher concentration of ORMUS in the Dead Sea and in like pristine areas in nature, and a lot of those locations, if you have some lower energy state of the spins for a molecule, maybe in an undisturbed location over long periods of time with like no radio frequencies or low radio frequencies, maybe you could get those weird chemicals to form in that pristine location over like millions of years. So like you have some excited state, but the difference between the excited state and the ground state isn't that much. But also it's hard to repopulate that. Like it's not just a like maybe it's like a thermal energy transition, but like once it's in that different state, it gets kind of stuck there or it's metastable and it's hard to flip it back for some reason. If you have a situation chemically that's like that, then over millions of years, if you have an undisturbed location, see a lot of this Ormus stuff, that's probably just like you're adding a base to an acid and you're precipitating out some material. I don't know. I don't know
Yeah,
about.
it's like they're taking the salt out of solution.
Yeah, because like you got a bunch of salts in Dead Sea water, and so if you have like calcium, you add oxalic acid to that, you'll have calcium oxalate crystals precipitate out. You're just doing chemistry here, as far as I know. But if there is something real to it, then it's possible that like over thousands or millions of years, you could have some chemical that's in some normal state that we know of, and then it sits there for a while and it goes into this other state, which it's hard to get back out of. And that like at least if there's something to Ormus, maybe it's there. As far as I know. Also, where's that dude who said he was going to get us some Ormus to analyze?
I don't know, but we're streaming live on his channel right now.
Oh, okay.
So we should ask him. Bernie, what's up, dude? He's got to be hanging out. I'll be jumping on here in a second.
Maybe.
So, yeah, apparently I didn't mean to. If we are streaming on his channel, if you didn't want me to,
Oops.
I'm sorry, but yeah, I don't know.
I
thought that he added it because I didn't remember doing that when I set it up. But anyways,
or our
totally
bad.
cool with that.
So yeah, I mean that's the deal with Ormus. Maybe it's literally like what they mean by orbitally rearranged is there's just some weird spin state there. So anyway, what else were we? What else was on the agenda? Oh yeah, the nonohydridorenates. Check that out. That one out.
What is it?
I sent you the thing in the chat. Not on YouTube. There's not going to be anything on YouTube about that.
No way. There's nothing on that.
You can just copy the thing from the StreamYard. I put the word there. There, potassium nonohydrorenate. Yeah, so this is a complex of rhenium with 9 hydrogens around it. And this is stable around like it's stable at room temperature and pressure. So you can get crystals of this salt. And so what I want to do is I want to try replacing the potassium with calcium, or perhaps with
these are the hydrogen crystals, man.
Yeah. So what I'm expecting is if we take that potassium and we replace that with some other ion, this will I expect that this will produce some sort of quasi-crystal phase. And yeah, like most things that have this high concentration of hydrogen are not stable at room temperature and pressure. So if we can replace the potassium with a much smaller ion, like erbium or europium, like the radius of those is much smaller, and so you get the hydrogen concentration is much higher, and then you compress that, and maybe you get metallic hydrogen superconducting properties, or who knows what, or the hydrogen could just destabilize out of the nonohydridorenate clusters. So
you also missed the invite I sent you in your email, Jeremiah.
So if people want to make these crystals themselves, the process is straightforward enough. You get some rhenium powder or rhenium metal pieces, and then you put them in concentrated ammonia, and you add some hydrogen peroxide, just a couple drops a day. It takes forever to dissolve the rhenium this way. but you eventually get it. And all of that rhenium, it becomes ammonium non-hydrogenate, and then you do a solvent exchange. So you want to use an ion exchange resin, and I don't know for sure if this thing is stable as an acid. I haven't heard anything in the literature about that. So the
But this, you
solvent,
can print diamond, right? We can 3D print diamond.
no, not this one. That's the polyhydridocarbine. That's a whole other.
Oh,
So yeah, and we're tooling up to do this. We have the chemicals we need to get this done. Yeah.
yeah,
So
this is cool.
basically, you get this from electrolyzing chloroform. So you make chloroform or iodoform or bromoform.
Is that legal?
What's that?
No, I'm sure it is. If you're not to make, is it legal to produce chloroform?
Many industrial, for industrial purposes, sure. I
Yeah,
mean,
that's not ether, right? That's not what the people
no, ether is different. Actually, chloroform is kind of dangerous because, like, at high enough concentrations, although like that wouldn't happen here. We have a fume hood. We've got a very large space with good airflow.
But all right, so
But like you don't want to like get stuck in a small room with chloroform because like if you pass out there, then like you can't get out of the room and like become conscious again. So like you might die. You might just sit there until you die because you're not going to become conscious while you're.
yeah, if you OD on chloroform and go into a coma, man, it's
Yeah, and then you're just stuck in the room with the chloroform, so you're just not going to wake up unless someone finds you, and
right.
maybe then they'll fall over too.
They'll see you, go try to rescue you, and that's how the nitrogen accidents happen. If you get like, you know, 100% nitrogen concentration from like a nitrogen tank leak, it happened.
Nitrogen narcosis, right? Underwater.
Yeah, the people passed out, and the guy like saw all the people down in like the pit, like all passed out, and the dude went down there, and as soon as he went in the pit, he took a breath of air and passed out because it sucked all the oxygen out of his lungs, instantly knocked out, and like by the time like they found the accident and cleaned it up, like 5 or 10 guys or something had gone in the pit and died trying to rescue the other ones down in the pit.
That's why they take canaries into coal mines, or they used to, because the canary has a faster metabolism. So if there's something dangerous, it'll drop first before you do. So then you know to get out of there.
Yep. Uh-oh.
Yeah.
Canary's down. Get out the coal mine. Yeah, but they also used to doctors used to OD on ether and chloroform back in the day too.
But yeah, I mean, you just put a little sodium chloride in this, and you electrolyze it, and you get some chlorine gas, which is not fun. But then you can like bubble that through some sodium thiosulfate or some other stuff, and then you get PHC on the other electrode. Then you put that in a vacuum furnace, and it turns into diamond-like carbon, and you can coat stuff with diamond-like carbon that way. And we're thinking of trying to see if we're going to see if we can dissolve the PHC in some solvent, because if we can make an ink out of that, then we can sinter we can just like we could 3D print diamond with that basically, or diamond-like carbon at least.
Cool. That's the. All right.
Oh, so Malcolm Bendel's thing.
We got a super chat. Someone paid.
Jeremy knows of a thing that works by similar principles. I'm not super familiar with the processes involved with that.
I had a buddy of mine.
So I know people were trying all sorts of things with car engines. I know some people injected water vapor along with the fuel, and they even like things with cars that like even they injected like excess electrons. Excess electrons sped up the combustion process and made internal combustion engines more efficient. So if you put excess electrons in there, if you put a little bit of water, a lot of things will catalyze improved results from internal combustion engines. And so this thunderstorm generator thing, like I don't know what it's necessarily doing in there, but they claim it's sort of like a better catalytic converter, and then it's a little unclear whether they claim it's actually putting out excess energy. So I don't know about that.
Yeah, I'm not quite clear on all the claims as well. I believe he's going to be at Tesla Tech this year, and I'm trying to, actually, I should have sent Steve an invite. I've been meaning to get him on to kind of pump that up and get people excited about that, because I mean the time's just flying by. It's already almost summer, so
yeah,
it's
wild, wild how the time flies.
Yeah, so I think we should absolutely be looking into this, because if it is something, the other thing too is I have some insight.
The one thing that's difficult is their system is very complicated. There's engines and there's geometries that they won't tell us about, and like specific geometries internally. Like they claim, oh, it's just a sphere, but like
it's like
the stuff we saw patented had very complicated structures to it.
But it's like a Hilsch vortex tube inside of a Hilsch vortex tube.
Yeah, I don't know. It's weird.
Right?
The vortex tube actually. So I don't know if that's so. Like they claim, oh, this isn't understood.
This is it, man.
I mean, they claim that it's not understood how it separates cold from hot.
Well, they got the cold fuel coming in, and the cold fuel comes in. It gets preheated before it goes into the engine.
But if you have an aerofoil, that separates cold from hot. Like if you just have a normal airplane aerofoil, the pressure reduces above and increases below, and underneath it gets slightly hotter, and on top it gets slightly colder, as a PV equals nRT. So if you have this vortex thing, and you're throwing air out to the edge, you're compressing that air, and then on the inside, you're making the air lower pressure.
Yeah, so
but they say the gas is coming out both ends, so there's some positive pressure on both of them, maybe relative to outside. But I would hazard a guess that the airflow rate on the cold side is less than on the hot side. But like, again, there's a ton of stuff to this system that it just makes it very difficult to test. It would be
it makes it hard to like do like a thorough analysis on it. But the thing
we could take the Hilsch vortex tube and check that out. But like that's known to work, right? So that component does make a temperature difference.
Yeah.
But then like they're putting UV light in there, so like just like the people who are injecting excess electrons to speed up combustion reactions, the UV light will possibly make excited electronic states in something that's, I don't know. There's maybe there's some weird condition where the water is somewhat fluorescent. I haven't heard of anything like that, but they might be inducing something weird like that. I know they have the ultrasound, so if you have like vorticity in the water, that might become phosphorescent, and then if that becomes somehow phosphorescent, then it could carry the energy into the reaction. I don't know. There's a lot of ifs here. There's a lot of ifs. So I wish them the best of luck, but I mean, we have projects that have a lot more certainty to them with a lot less complexity. And so we gotta start with those, I would say, and not necessarily this. But I'm sure like we'll get to the point where we can test this out. If anything else functions as we think it may, then like I'm sure we'll have plenty of funding to look at this too. But this would not be my first choice if there's something to look at.
Yeah,
so sorry for the long-winded.
We got lots of cool things that, inventions. Yeah. And my friend was working on this. He has a patent on this same kind of thing from 10 years ago. So if Randall Carlson wants some better, more up-to-date ideas and information and technology, he should probably talk to us.
Yeah, I mean, I would say so as well. So anyway,
I wish these guys luck with this thing, but I mean, this is not anything new, and we are.
Yeah,
Like,
and I mean, it looks like it's just some sort of alternative to a catalytic converter, if I'm being
it
honest.
cleans the fuel. Yeah, sure, you got a cleaner fuel because you're cooling down that you're using that condensation that back. But how long does that actually last longevity wise? Because they only show these things running for like 5-10 minutes in a video. I've yet to see them hook up to a unit and come back after a year and see like what it actually has done and if, what the wear and tear on the whole design and system is.
And I would wonder if any of the guys working on this would actually like take that bet, like to take the exhaust from the tailpipe and put a mask over their mouth with that. I don't know if they would actually take that bet. I would be willing to bet they wouldn't, because they were saying, "Oh, it makes perfectly pure air coming out the other side." I don't know about that. That seems
we
like
just
very
gotta keep
long
doing
time.
what we're doing, man. People will eventually come here when they realize like this is. All right,
Anyways,
let's. I had a question. Another super chat came in while we were off on this tangent.
so
Can you explain the Bueller find a little more in depth? He achieved more than 1 gram.
yeah, I don't know. We're trying to replicate their result. Jeremy, maybe you can show the 3D models. But
Yeah,
I
yeah.
mean, so the idea is you have 2 capacitor plates. On one side you have a monopolar electret. On the other side you have a high dielectric constant material. And so Charles Bueller has a stack of. He has a monopolar electret on one side and this high dielectric material. And when you put an electrostatic charge on this block, then the electrostatic field lines will want to go from this thing up and around to the backside of this thing. And so the forces exerted by the electrostatic field are normal to the electrostatic field lines. And so if the field lines all impinge on this side and then they impinge on the opposite side, then the effective force on both plates is in a specific direction without necessarily a counterbalancing force. And so there's a lot of weirdness to that needs to be looked at in more detail if it's real. So the main gripe about Charles Bueller's work is they have this capacitor plate on on a pendulum or like on a cantilever. And so they're electrostatically charging this thing, and they're watching it change its cantilevered state. So, but with large electrostatic, I mean, they're only charging this thing up with 10 volts, so it's not a very high voltage. But they still have a large electrostatic field on the electret that they're using. So, in principle, if this thing has a large electric field involved with it, this thing could be attracted to something else in its near environment. Especially if you have a small vacuum chamber, it could be attracted to the wall of the vacuum chamber. I think Jeremiah made a video at Mark Sokol's lab where they had a monopolar, or actually I don't know if it was monopolar, but they had an electret made out of acrylic, and that electret was sticking to the metal plate below it. And so there's clearly a force that can be exerted between the electret, especially if it's a monopolar electret. Its charges aren't shielded on either side, so it's like a chunk of charge in this environment. So, so they have a cantilever set up, or so they claim, and so they're measuring the deflection of this cantilever, or so they claim, and I don't know. I think that's not foolproof. So what I want to do is I want to take a bunch of these flat pieces of electret and in capacitors, and I want to charge up these capacitors. And if what Charles Bueller is saying is correct, this thing should spin. The setup that we have looks like a Crookes radiometer, so that whole thing should spin, and it should just keep accelerating if this thing is indeed imparting a force. And because it's symmetric about an axis, if there's an attractive force to something in its environment, then it's roughly canceled out. So it might, if there's an attractive force to something in the environment, it will align like a compass needle, and then it will kind of settle. It will go back and forth a little bit, but it will ultimately settle at that location. But if we're actually seeing a propulsive force, then these two plates, which are opposite of each other, should start running away, accelerating. Yeah, it would effectively. It's a new type of thrust. If that, so it's a propellantless propulsion, allegedly, and it. Well, yeah, I mean, this asymmetric field shape begs some deep, deep questions about what the nature of inertia is and how inertial mass relates to electric fields.
Oh wow! So Chris Leto had this on 7 days ago.
Oh yeah, it's starting to go viral. Charles Bueller's talking to a lot of people now about this.
It's awesome, man. We
Yeah.
started it.
Yeah, I mean, it's pretty awesome. Yeah, we were the first on that train, but we might be the ones to end it if the device doesn't work. I mean, I'm happy to get some feedback from Charles and his team. I think one of their team members was like, we want an NDA before we share anything, but like also, like if we fail to replicate, that won't look good for them. So they need to like. I don't care about making an optimal one, but if they can share a few secrets for making an acceptable one, such that other people can test this, but it's like behind their best design, then I'd be perfectly fine with that.
Yeah,
I think it is more valuable.
Maybe if we just, instead of an NDA, we sign a non-compete order, a non-compete.
I'm fine with that. I mean, if this is legit, then like
because we're just trying to replicate it to show everyone this is
like
legit.
Ultimately, if we can replicate this really gets off the ground, changes the world. I mean, it would benefit me enough just to be living in a world with that sort of technology. Like we could be mining asteroids. I want to make an asteroid homestead. That's what I want to do. Just make a little farm with a geodesic dome on an asteroid. That's the life.
I guess, man. I just want to live in the forest somewhere.
That'd be nice. You could grow a forest on an asteroid if you want, though.
Hell yeah, we're live, man. No NDAs. Yeah, I don't want to sign NDAs because like I run a channel for disclosure, and if I can't talk about stuff, man, that's not disclosure. It's the opposite of what I try to do here. So
yeah,
hope people understand that we're trying
it's not smart. And yeah, I mean, it's beneficial to them to get these replications done.
And yeah, we've been working on this, man. This is all stuff we've been working on. We're getting it all done. It's all coming together finally.
Yeah, I mean, Jeremy made a glove box.
I've been talking about quasi-crystals for 20 years, and now I'm finally printing them and building them, and we're gonna make some actual crystals and
and hopefully we can get some XRD on. If anyone's got an XRD lab and they want to look at rare earth nonohydridorenates under XRD, we expect that some of those will be quasi-crystals, and that would be a cool paper to publish. And if those are quasi-crystals, well, even if they're not, if we have some nonohydridorenate with a denser ion, so the renates are more closely packed together, then that might be one of the densest forms of hydrogen achievable. I think erbium deuteride is denser, but you have more erbium per hydrogen than with nonohydridorenate. Like I think one of these nonohydridorenate salts is probably going to be pretty darn close in physical properties to metallic hydrogen, possibly, or something along those lines. I mean, there's nothing else that's stable at standard temperature and pressure with that much hydrogen compared to other elements. There's no contest. So, I mean, even like if it requires some minor pressure to go to a metallic hydrogen sort of state. Yeah.
Heck yeah, Ken. As I mentioned before, we don't need money. We need lab equipment, and we need experts with time and knowledge to kind of help out with the meetings and the
Money
design.
helps with getting those too.
Money helps
but
with getting those people. So, but if you
Jeremy, we should really think about setting up like some sort of like tax deductible donation thing through the business. And
yeah, well, that's what I'm saying. If people just bought us gifts, right? If I just said like, instead, because we got to get the money, then we got to cash out the money from investors. So we have to pay taxes on the income, then we have to buy the products, and then we have to so it's like
well, we got a business guy. We can figure that out. We
yeah.
can.
What the idea is that if people buy us these things as gifts, it's like it's all like community donated. So like we don't have to claim any of that on our taxes if we just put it up on a website and people just buy it and send it to us. And it's
Yeah, I think that we should keep all our ducks in the row. We don't. I mean, like with the deep state,
you never know what the government.
Sure, they'll probably at the end of the day they'll probably like make up a reason to go after us, but we don't want to give them an easy reason. Like we want to do things
right. Yeah, I guess that's true.
do things right as much as possible.
That's what I was saying. Almost we should have like a members only. Maybe I'll do a video for members only because we're doing the memberships. I just got a new member here, right? So what we'll do a members only meetup once a year where people can come in, and if they want to donate big money and help out. Kalex, thank you for becoming a new member.
Nice.
Awesome. Glad to have you on board. And I believe that's the only new member tonight. I don't see any other ones, but thanks again to Harry Toe for the $10 super chat.
Nice.
And, Kent Racer gave us $5 twice, I believe. Yeah, here's another one.
Okay, explaining Bueller in a little more. Oh, did we already answer that one? I don't know.
Yeah. So did we answer your question? Did we give you $5 worth of response? Are you $10 worth? Are you awesome? Because if not, we can talk about it some more. But basically, it's these electrets that are replacing, like Thomas Townsend Brown had these lifter idea and stuff, and now Charles Bueller has kind of gotten expanded upon that with he went over all the Townsend Brown work in his lecture. If you go back,
it's sort of like one side of this thing has a very high positive electric susceptibility, and the other side of it has a very high or relatively high negative electric susceptibility, and that combination on the plates causes this force distribution that's weird. And yeah, this is saying something extremely deep about what matter is and what inertia is, because like we've seen weird effects like this in the past, like in the Wu experiment, that the WU experiment. I think actually, what's the guy's name? Blanking on the name all of a sudden. Dave Zed or Dave Rossi or
Dave Zed, yep.
Yeah,
Dave
so Dave Zed's he pointed us to the Wu experiment, and so this is very interesting. So when you do nuclear magnetic resonance on cobalt 60, so all the nuclei are oriented in the same direction, then the beta radiation emitted from the cobalt 60 is all mostly in the same direction, or within some degrees, so you can actually, in principle, you can create a rocket. Actually, this would be really cool for like ion propulsion. If you could do NMR or dynamic nuclear orientation on radioactive nuclei, and then they all decay in the same direction. So now you're getting like a megavolt level beam of particles in a single direction for years and years, or as long as you care to use the thruster at least. And so the total power, I mean, it wouldn't be externally powered; it would be powered by the radionuclide or whatever. But yeah, I mean, ultimately the decay pattern is dependent on the angular position of this nucleus relative to some orientation, and so that breaks some symmetries, um, and that's saying something similar as well. Uh, so like in the Yang-Mills theory, particles are solitons. Particles are a type of soliton, and solitons are nonlinear wave equations. So it's like a trapped light with a nonlinear addition to an otherwise linear term. So you have some photon that has a sufficient energy to become kind of stuck to itself, or this nonlinear behavior starts. And so with a nonlinear wave equation, if you apply these weird external fields to it, um, just like something in Conway's game of life, it will propagate in some direction potentially, without necessarily the requisite uh, momentum transfer that we would expect.
Interesting. Yeah, so like the other question from Esoteric Gold was talking about the Ormus stuff, but right before that, I had a question about the VEM, Paris and the VEM drive. So we had scheduled to have a meeting with David Perez to go over some of those details and stuff, so that I could help replicate this better. And he'd like backed all out, was like, that's proprietary information, and it's like, dude, I'm just trying to replicate your stuff, not steal it.
Yeah, this is like, it's silly because like these teams are going exactly the wrong direction. Like, if they really want this stuff, like,
We got to open source it. We got to all work together, man.
Maybe they already have a deal with like the military or something. I don't know.
David,
but if they really want this stuff out there, if they really want to get investors,
David had admitted he wants funds, he wants patents, and he wants to make money.
See, that's the wrong reason. Like, if you do that, then the deep state will own you, and then this stuff will never see the light of day. Like they'll take ownership over the patent.
It's disappeared so many times.
It never works. It never works. Maybe they'll end up with like a small million. They'll get a couple million for their effort, for their trouble. Right. And then they go off and like sip pina coladas on a beach the rest of their life and make no real improvement to humanity.
Yeah. Hey, but
that's the deal with the devil.
The devil will take care of you in some ways for your time on Earth, and then you pay him back.
Oh no.
Papa Legbo.
Anyway, was there another question? I mean, we'll see. Like, it's with David Paris's thing. Like, we'll see. We'll try our best to replicate it, and like, if he's not helping us, then I don't know. Maybe he'll be fine, but the rest of humanity is worse off for that lack of willingness. I mean, Charles and the rest of these guys, they gave us enough information to at least.
We asked some good questions. We got enough that we can go on, and now it's just a matter of getting all the rest of the materials here. They should be here by the end of the week to get that rolling. I can't wait. And then we're going to do the. You want to give it? I'll give it a quick tour and walk around, and then we'll wrap this up.
Sounds good. Yeah, it's a little messy at the moment, though. We should really do a lab cleanup soon, especially before the summer interns get here. So yeah, we got the vacuum chambers. Oh, we should pump down that vacuum.
Yeah, why don't you? We can do that. We got a glove box that I made. I designed these special rings. Work with toilet flanges because it's a good size to put your hand through, and for the glove. And so we can do the electrostatic stuff in there. That's really loud. I'm going to get away from that. And I'm working on this design now. We're going to take this flange off of there and put this on with the jar on top. I'm going to seal this jar, the mason jar there, so we'll have this as our vacuum chamber. And I'm going to have our little pinwheel apparatus that I showed earlier here. A version of this go way up inside It'll be way taller than this. But a version of this will go up inside and sit up in there like the radiometer.
We're definitely going to have to clean that thing off with isopropyl or something before we put it in high vacuum.
Yeah.
And this block at the bottom will need a redesign. That'll just block the airflow.
Yeah. No, we're gonna. I agree. No.
Yeah. Anyway,
So,
yeah, that's this is gonna be awesome. So this will fit here. This was for a separate experiment previously.
we're gonna have a high voltage electrode connected to the top here through a wire that goes up through the middle of that.
Yeah.
I have a mock-up design here so that people can kind of see how that goes. Oh wait, here, I'm not even showing off my screen full screen here. What am I doing?
Oh, by the way, just a cool thing. I don't know if anyone has shown ammonium metaniobate online before, but vanadium, ammonium metavanadate is a common material in vanadium chemistry, but I added just a tiny amount of ammonium metavanadate to this, and then I kept adding peroxide, and this is an ammonia solution with niobium powder at the bottom, and it's quite a beautiful purple color actually. So we're going to be doping LK99 with niobium because I suspect that it will improve the performance.
Very
We got
cool.
all sorts of, all this stuff is going to be for LK99 replicate. We're tooling up for a major bunch of like LK99 replications with
Heck
different. Yeah, this is going to be fun. We'll see. The copper phosphates and hydroxides are ready. Lead oxides ready. Lead sulfates ready. We just need lead phosphate. And then we're all set to go.
Once again, thank you to everyone who's been supporting this channel since day one. All this wouldn't be possible without your help and support getting us to this point. So thank you all.
I'll show them the metavanadate.
Very cool.
Yeah, so this one's ammonium metavanadate, and it's a nice yellow color. And if you can see there's some like really nice, the shapes don't come out there, but like they have some really beautiful geometric shapes. Maybe I'll
you can
take some.
Can't really see it on the camera.
Yeah, I'll take some.
Right here.
I'll take some close-ups over the microscope later. But yeah, this ammonium metavanadate crystals, very beautiful. Got like an orange color with a gradient to them. Like it's got that like what's the effect?
We don't have any other choice.
It's like mica. It has that Bragg reflector surface to it.
Yep, it's got the Bragg reflector, dielectric mirror. Iridescence, yep.
Yeah.
Heck yeah. All right, guys. Well, have a great night, and thanks for watching. And we'll do a stream soon with some more updates. I'm sorry I couldn't be at that event tonight in Somerville. If anyone went, I'm hoping to link up or anything. So later, guys. Have a good night.